This is a help video for the DC Operational Amplifiers game in Circuit Tutor, Level 3, Problem Type 3. So I'll go ahead and go into that game. And as always, we do recommend that you review the introductory tutorial, which will have a lot of information about how to solve these types of problems and the basic theory that's involved. Also, it's strongly recommended to look at some examples before you begin working problems, as that can help a great deal in understanding the solution procedure. So we're going to go ahead now and go straight into a problem at level 3. Okay, and we have the instructions here, just general instructions on writing equations, which you can access at any time from the help menu. Now this circuit is a bit unusual. You may not have seen one like this, where the input, the voltage source, is actually connected not to ground, but to, on one side, to an input of the op-amp, and the other side here to some resistors that are also connected to the output. So this is a bit of an unusual type circuit, and we'll explain the purpose of it a little later. But basically what this is doing is it's taking an input voltage, and then the output current here is actually IA. This does not have an output voltage really, and so it's converting voltage to a current. This is called a transimpedance amplifier. So in any case, we can go ahead and solve this by standard methods. You could actually solve it by inspection, which maybe I'll talk about a little bit at the end, but let's just go ahead and do the straightforward method. So since we have a voltage source, we will need a voltage constraint equation. Since we're going to do a nodal analysis, remember that nodal analysis is virtually always used for operational amplifier problems because of the fact that they may be non-planar and they may have, well, they do have hidden circuitry inside of the op-amp itself. So for our voltage source, we have the 1 volt source, and that's basically relating voltage at node 1 to voltage at node 3. So that'll be a difference of 2 node voltages is just going to be equal to the value of that source. And so that's going to be node 1 on the positive side minus voltage of node 3 on the negative side, and that will simply be equal to the value of the source, which is 1 volt. So we'll go ahead and check that, and that is correct. Now the next type of equation that we always need for an op-amp circuit is called the input constraint equation. This is unique to op-amp circuits, and it basically expresses the fact that due to the negative feedback from the output back to the negative input, in this case via a voltage source, which again is a little unusual, that means that the op-amp is, due to its very large or virtually infinite internal gain, it's going to force these two inputs to be at the same voltage. Again, this doesn't happen internally in the op-amp, it happens via this external feedback path. And for more detailed discussion of that, you can look in the introductory tutorial as to how that happens. It's somewhat mysterious, perhaps. So what we need to say, therefore, is that these two nodes have the same voltage. One of them obviously is ground, so that means that V3 simply has to be 0. It has to have the same potential as ground, even though there is not going to be any current going into the input terminals of an op-amp. Remember, it has virtually infinite input resistance here, or impedance, and the output has essentially 0 impedance. This is connected to a voltage-controlled voltage source, which basically amplifies the difference between these two input voltages with an infinite gain, meaning that for this to be finite, this must therefore be 0, as we're expressing here. Okay, and now you might say, well, okay, what about KCL equations? So let's go ahead and do that, since that's sort of the core of nodal analysis typically. And we could say, well, which nodes can we write a KCL equation for? So if you look at node 1, can we write a KCL equation for that node? So think about that for a moment. So hopefully you have concluded that no, we cannot write a KCL equation for node 1 because it's connected to a voltage source. And remember, voltage sources have a fixed voltage, but their current is whatever it needs to be, and we don't know what that is at this point, at least not without some additional reasoning. So therefore we cannot do that. So what about node 2? Think about that one for a minute. So if you reflect on what I told you about the op-amp, it has an internal voltage-controlled voltage source connected to the output, the other side connected effectively to ground, although there's no real ground connection in the op-amp. There's really just plus and minus power supply connections, which are not shown here explicitly. Because of that, this is like a voltage source, the output, and we don't know its current. Therefore, we cannot write a KCL equation for node 2. So that leaves one more node, namely node 3. So let's reflect on that one. So once again, because it's connected to a voltage source, we cannot write a KCL equation for node 3. So it seems like we can't write any KCL equations, and yet, do we have enough equations? Well, we have 3 node voltages, V1, V2, and V3, and yet we only have 2 equations. So that might leave us a bit stumped, but we remember there's always a magical solution to that, or maybe not really magical, but a trick solution, which is that we need to form a supernode. And in this case, since we have a voltage source, we can form a supernode out of node 1 and node 3 and write a KCL equation for that. Now, you may well say, well, do we really need to do that? Because after all, there is no current through this source. And that is true because, remember, this has an infinite input impedance. So there's actually no current going this way. But nonetheless, in order to use the program, at least in this way, we have to write that supernode equation. So we're going to select nodes 1 and nodes 3 to form a supernode and write a KCL equation for that. Without doing this, there's no way to solve the problem. At least, I mean, there is a way to solve the problem just by inspection, but I'll come back to that later. Okay, so the current here is 0, so we don't need to worry about any currents involving node 3. And node 1 has 2 currents, namely leaving it through the 2 ohm and leaving it through the 1 ohm, or entering, whichever. So the 1 ohm current, that's going to be a single node voltage since the other side is connected to ground. Here we have 2 different node voltages, so we'll need a term like this, and the sum of those equals 0. So now, filling in the blanks, we have V1 divided by 2 ohms, and using the tab key here to go between entry fields. And then here we have V1 minus V2 divided by the 1 ohm. That's the current going upwards here in the opposite to the direction of I naught. So we'll check that. And that is in fact correct. So now we have the 3 equations that we need to solve for our 3 unknowns. Again, always count your equations and your unknowns before you say there's no more equations. Otherwise, you'll just have to go back and do it. Okay, so now we do need the SOT variable equations also. We have 2 SOT variables here, both of which are currents, and they're both branch currents. They go through a single element, not through a wire, say. So the first one will be IA, and that's a current through a 2 ohm resistor, so we just need Ohm's law there, and it's going to have the form similar to what we wrote in the last equation, just 1 voltage divided by that resistance. So it's V1 divided by the 2 ohms, and that's the current, again, going in the direction of IA. We do have to, of course, pay close attention to polarity. So remember, current always goes from high voltage to low voltage, presuming that this is a higher value, which it may or may not be. Okay, so we'll check that. Oh, sorry, I forgot to put in my equal sign there, so we'll put that in. So we have a full equation, and check that. Okay, and then we need an equation for I naught, the other SOT current. So we'll click that variable. We're not allowed to write an equation if you try to write that IA is equal to I naught, which actually is true if you think about it, because there's no current going through here. So actually I naught and IA have to be the same value, but it won't allow us to do that because we're only allowed to put one SOT variable equation. Normally they're not equal to each other, so it doesn't allow that. But we can express it directly in terms of Ohm's law, so we don't need to do that. We can simply write V2 minus V1, and the water flowing downhill, if you will, in this direction of I naught. Again, we have to pay attention to the polarity. If the current pointed up, of course, these voltages would have to be reversed, or we'd have to put a minus sign here, or maybe out here. Okay, so that is correct. Now we've written all the equations we need for this circuit, and so we'll say no more equations. Okay, so now we need to organize these into simplified equation format. So we'll do that here. And first of all, we have V1 times 1 minus minus 1 times V3 is equal to 1 volt. So that's our first equation here, fitness coefficients. V3 is 0, so we could put 1 or really any number times V3 is equal to 0. And for the third equation, we have V1, we have a half V1 plus 1 V1. That's, of course, 3 halves, or just 1.5 V1. Or we could write it as 3/2 if you like. And then minus V2 over 1, so that's just a minus 1 here. And then the rest of that is just 0. So that should complete the equations. We just check those. And of course, we could have also skipped to the final answers if you know what those answers are. And at the end, maybe I'll show you how you could have actually seen that by inspection and maybe short-circuited a lot of this, no pun intended. Okay. Now, we just have to put that into the matrix form, and instead of retyping, we'll just use the copy button there, and that will therefore be correct. But we're not going to really want probably to use matrix equation. Okay, so it advises us now don't use MATLAB or a calculator to solve that. Instead, do it by hand the way you'd have to do it on a test, for example. So we know that V3 is 0, so that's already entered here. And then we can solve for V1 just using this equation and the fact that V3 is 0, so we imagine that being gone. So V1 is just 1 volt. So that's something we just see really without writing anything. And then for V2 now, we have to come down to perhaps this equation, the third one here. And that says that V2, if we bring that over to the right-hand side, is just equal to 1.5 times V1, which is 1.5 times 1, or V2 is just equal to 1.5. And that's should be complete now, so we can just, and again, we could have skipped the step if we know the final answers, but that is correct. And then the last step is to use these values to find the sought variables IA and I0 in this case. So that's pretty simple. So IA is just equal to V1 divided by 2. And remember, V1 was 1, so that's going to be 0.5 amp. And you might remember, as I already said, that these two have to be the same. So we already know this has to be 0.5 amp. But if you didn't remember that, you could have also just taken V2 minus V1 divided by 1. So that's 1.5 minus 1 is also 0.5 volt divided by 1 ohm is 0.5 amp. So we'll check that. And that is correct. And now it's making the PDF transcript of our work. And we can access that from the review work button for purposes of review or studying, which is always, of course, a good idea later. Now, we could get a detailed explanation of this also. So I'm just going to show that for completeness here. And it shows how the KCL equation is formed. Now, one thing I'd like to just go back and just reflect on this circuit and its purpose. So we know right away that because this is 0 volts, this has to be 0 volts also. So we could have then deduced, well, this voltage here has to be 1 volt. And from this being 1 volt, we could have immediately seen that since this is 1 volt, this is 2 ohms, that has to be 0.5 amp for IA. And because no current goes this way, you could say, well, this also has to be 0.5 amp. So we really could have just written I0 and IA as numerical values at the very beginning, and that would have been accepted, and then you wouldn't have had to write all these other equations. And that's a perfectly good way to solve this circuit. So sometimes you can just use your own good sense about circuits to understand what's going on. But again, you have to use the principles of what op amps do. And we also might ask, well, what is this circuit for? Well, its purpose really is to convert a voltage input to a current output. This is called a transadmittance. The gain is a current divided by a voltage, which has units of Siemens. And you see, whatever the voltage is here, basically that voltage divided by this resistance is going to be the output current. So by adjusting this resistance, we can make that current be pretty much what we want it to be. And so it's a convenient way of converting voltage to current, which is useful in some types of circuits. So this is a special purpose transadmittance amplifier. Okay, so I'm just going to close that now. And again, if you wanted to review your work, you can do so here. And that completes this problem.